Right now we're going to talk about periodicity, and periodicity is just trends on the periodic table. So as you move over, this increases. Talked about it a little bit with ionization energy. You know, as you go from left to right, the ionization energy tends to increase. So elements on the left side of the periodic table would be easier to remove their outer electron than the elements on the right side of the periodic table that are in the same row. And there's two guiding principles really that make all the difference for periodicity. So if you know these, you can explain any of the periodic rules, and you can also figure out what they are just from knowing this. So the shielding effect, we've talked about it. Successive shells are larger than the previous shells, and so that means the electrons start moving slowly farther and farther away. With each new shell you add another distance from the nucleus. Coulomb's law, it says they're going to be having less of a force of attraction to the nucleus. And also as you get farther out, you're going to have inner shell electrons, and those are going to block the outer shell electrons from feeling the attractive forces by the nucleus. So it's going to provide that shielding. So the shielding effect, which is repulsion from the inner electrons, reduces that attraction between the outer electrons and the nucleus. Fancy way to refer to that is the effective nuclear charge. So when we're talking about things in this unit, there's really three terms you need to remember. Coulomb's law, be able to explain that and use that as a justification for certain things. Shielding effect, so be able to talk about that. And now the effective nuclear charge. The effective nuclear charge, which is symbolized Z subscript EFF for efficiency, it's really just a conglomeration or a joining of Coulomb's law and shielding. So it kind of weighs those two. So yeah, the electrons are feeling that pull from the protons, but they're also feeling that repulsion from the inner electrons. How do we kind of join those two? We call it effective nuclear charge. The equation don't concern yourselves with so much. It's more about, it all just kind of deals with the electrons, where they're placed, and then the nucleus as well. So let's say we have an atom and it has 6 protons in the nucleus. That would be carbon, so it would have 2 electrons in its first shell, and it would have 4 in its second shell. Okay, so these 2 electrons, or these 4 electrons on the outside, they're going to feel some attraction for the nucleus, but it's going to be slightly diminished because of the shielding from those inner electrons. So we're going to have shielding from these guys right here. They're going to shield them, and we also have the distance from the nucleus. So what happens if we go one step over on the periodic table, and now we look at nitrogen? So nitrogen has 7 protons, 7 electrons. So if we look at the electrons, the outer row electrons that are in nitrogen now, we see that the distance between the outer row electrons and the nucleus is the same. The shielding is the same because they both only have 2 inner electrons. So the difference really between these two would be the number of protons. So since this guy has 6 protons, that means you have 6 positive attracting these electrons out here. This guy has 7 positive attracting these electrons out here. So all of these electrons, all 5 of these electrons are for the most part the same. They're the same distance from the nucleus. They have the same shielding. But this electron right here, it feels the pull of 7 positive, whereas this electron only feels the pull of 6 positive. So we would say that the effective nuclear charge of carbon is less than the effective nuclear charge of nitrogen. So even though they are both neutral, and they have a 1-to-1 ratio of protons to electrons, the shielding's identical for both of these, the distance is identical for both of these, but since the protons here have more pull power, you're going to have a higher pull on these outer electrons. This is why it's easier to remove an electron from carbon than it is from nitrogen. So one of these outer row electrons, you could take this guy from carbon a lot easier than you could take this guy from nitrogen. That's the ionization energy. So that's why ionization energy increases as we go from left to right, because the effective nuclear charge increases. An effective nuclear charge can explain these 4 different forms of periodicity. So these are physical and chemical trends that occur as we move across or down or over or up on the periodic table. So we're going to talk about atomic radii, ionic radii, ionization energies, and electronegativity. All right, atomic radius. The way they measure atomic radius is they would take two atoms that are bonded together, so like oxygens, two oxygen atoms, and they would take them when they're bonded together because they actually kind of squish it, and they use that to measure it. So they'd measure it from one nucleus to the other. Rather than just doing the radius of a single circle, they would measure from here to here, so from middle to middle, and then divide it by half. So that distance divided by 2. And of course, these are very, very small distances because we're dealing with atoms here, so they're extremely tiny. And if we look at the trend indicated over here on the side, the atomic radius, so the distance between those two right there, will increase as you go down, and it will decrease as you go over. All right, this might be a little bit counterintuitive. Remember, as you go over, the number of electrons and protons gets larger, but yet the atomic radius decreases. So atoms actually shrink as you go from this side to this side. So that means sodium would be larger than neon, and potassium would be larger than bromine and krypton. So it decreases as you go from left to right, even though the numbers get bigger. This one right here should make sense, because remember, the row number tells us the row number of the outer electrons. So this first row would be the n equals 1, n equals 2, n equals 3. And so that means as we go down, you're going from a single shell of electrons to 2 shells to 3 shells. And you see how that gets bigger and bigger and bigger as you start adding those concentric circles. And so we're going to increase the radius as we go down on the periodic table. The decrease, as we go from left to right, that deals more with the effective nuclear charge. All right, so let's compare sodium to argon. Now these are definitely not drawn to scale because according to the periodic trend, argon should be smaller than sodium. So this is where it might seem slightly counterintuitive. If you look at these, well, I mean, check out this guy, 11 protons and only 11 electrons, only one in its last row, whereas this guy, whoa, argon, it's got 18 protons and 18 electrons, 8 valence electrons around that outer shell, but yet, according to this periodic trend thing, we're saying argon is smaller than sodium. And it actually is, and it's because of effective nuclear charge. So remember, the whole idea of Coulomb's law is there is a force of attraction between this electron and the protons in the middle. That's what holds it together. If there was no force of attraction between these two at all, that guy would just fly off naturally. But we know it doesn't. It is on sodium when sodium's in its pure form, but it's easy to remove this electron because of a weak ionization energy. Same thing with these electrons in argon. So they're attracted to the nucleus, and that's what kind of holds the whole thing together. And so since sodium has a smaller effective nuclear charge, so the effective nuclear charge of sodium would be less than the effective nuclear charge of argon. That's because sodium has less protons in its nucleus to pull on its outer electrons, whereas argon has 18 to pull on its outer electrons. And so what that means then is this nucleus would have less of a force on that nucleus. And so this guy, argon, is going to be able to pull its electrons in a little bit tighter. And so when it pulls those in, it's really squishing down the nucleus. So as a result of this higher effective nuclear charge, it's able to pull its electrons, outer row electrons, in a little bit closer, which is going to squish this circle down and make the nucleus, or make the radius, get smaller. So this is what happens as we move from left to right. The effective nuclear charge increases, and the pull that the nucleus has in these outer row electrons is able to pull it in a little bit tighter. And so as we move from one element to the next, to the next, to the next, to the next, we're slowly dragging those electrons in closer and closer and closer and closer, bringing down the nucleus in size. So here it kind of is. As we go down a group from top to bottom, you're adding those new shells, so new principal quantum numbers, the n equals 1, 2, 3, 4. So by default, it's going to be larger orbitals. If you put a circle around a circle, the second circle has to be bigger. Valence electrons have more energy, are much less stable, therefore they're going to be further away from the nucleus. So as you add them, they get farther and farther away. Also, those outer electrons, they're going to experience more shielding and a decreased effective nuclear charge. So we're just talking from top down. And so therefore, that's going to go farther and farther away. So this is just Coulomb's law. As they get farther away from the nucleus, they're going to feel less force, and so therefore they're going to spread out a little bit. But here's a recap then on the left to right thing. So as you add valence electrons inside the same shell, so we're not adding any more rings as we move from left to right. Instead, we're just adding more electrons to the same row. So the shielding effect experienced by all outer shell electrons would be similar. So the addition of protons, therefore, is going to increase that effective nuclear charge on those electrons. So as we move from left to right, once again, Coulomb's law, they're going to feel a stronger force for that center, and so it's going to pull in those outer row electrons a little bit more and more and more as we go from left to right. All right, ion formation. So you should remember this. Metals form cations, nonmetals form anions. Metals lose electrons to form those cations, so what's happening is, like potassium loses one electron, so here we show electron as a product because it's being produced and packed off. And if it loses one electron, well, it's going to have just as many protons, and so it's going to be positive. Nonmetals, on the other hand, like chlorine, they gain an electron, so here we show it being added, and that's going to once again throw off that balance, and so it'll wind up slightly negative. And of course, the periodic table can be divided into metals and nonmetals based upon that stair step. So all of these guys, and notice there is a lot of metals on the periodic table. Most of the elements on the periodic table are metals. So all of these are going to form plus charged cations. And then the nonmetals, smaller amount of them to the left of the periodic table, along with, or to the left of the stair step, along with hydrogen, they're going to form our anions, so our negatively charged guys. So our metals, these will all lose electrons, these will all gain electrons. Noble gases, however, they obviously don't lose or gain electrons, so they would not form ions at all, but they're still considered nonmetals. Hydrogen, it actually swings both ways. Sometimes it can form a positively charged, and sometimes it can form a negatively charged, but it's considered overall a nonmetal because it's not metallic. We don't think of hydrogen as a solid. So the loss and gain of electrons forms what we call isoelectronic species. So iso, that's a fancy word for equal. Electronic, think electrons, and species, similar things. So isoelectronic species are things that have the same number of electrons. So argon, which has 18 electrons total, so 1s2, 2s2, 2p6, 3s2, 3p6. If chlorine, which normally chlorine would have 17 electrons, but if it gains one electron, it now has 18 valence electrons, just like argon, which means that it now has the electron configuration identical to argon. So we would call these two guys right here isoelectronic species. If sulfur gains 2 electrons, well, now it has the same electron configuration. If calcium loses 2 and potassium loses 1, that means all of those right there are going to have the same electronic configuration, which means all of them are isoelectronic. And what we can see here too is, remember, the noble gases, they're noble, they're powerful, they don't need anyone, they're already stable. Elements want to be like the noble gases. So the reason chlorine gains an electron is so it can have the stable configuration of argon, sulfur gaining 2, calcium losing 2, and potassium losing 1. All of those to achieve this noble gas notation, which is stable. Now let's think about what this means in terms of radius. So if we're losing and gaining electrons, what's that going to do to the effective nuclear charge? So here's a normal chlorine atom. It's got 17 protons, 17 electrons. These outer row electrons right here, chlorine's going to have a pretty high effective nuclear charge because it's got 17 protons pulling on the 7 outer electrons. It's going to be much smaller than the atoms to the left of it on the periodic table. However, if we throw another electron on here, so if we turn this from chlorine to a chlorine anion, that means one more electron being added. So 8 electrons total. We now have 8 against 17. Before we had 7 against 17. Who's going to feel a stronger force of attraction? Who's going to have a higher effective nuclear charge? Keyword there is effective. So if this nucleus is pulling on 7 electrons or 8 electrons, yeah, it's going to decrease the effective nuclear charge. So the power that this guy has, it's no longer going to be as strong. And so as a result, these electrons right here are going to end up going out. That nucleus no longer has as much power as it once did. Its effective nuclear charge goes down, so the radius increases. Let's compare that to sodium. So sodium has its 1 valence electron and its 11 protons. Normally, it's going to be much larger than chlorine because its effective nuclear charge is going to be weaker than chlorine's effective nuclear charge. However, if it loses its 1 valence electron and turns from sodium to a sodium cation, so that means losing that guy, which means losing this entire shell. Look at that, the radius just got smaller. Not only that, but now we have 11 protons and 10 electrons. That's going to increase the effective nuclear charge, which is going to suck those rows in a little bit more, thus decreasing the radius. So sodium gets smaller in its atomic radius because its effective nuclear charge goes up and its number of shells goes down. So in a nutshell, all due to the effective nuclear charge, anions get larger, cations get smaller. So here's an example of this. We're looking at potassium and strontium here. So potassium, it normally has a radius of 227 picometers. Pico, it's one of the prefixes, well below nano and milli and all of those. So 227 picometers normally. When it loses 1 electron, so it's got 1 outer shell electron, it's going to lose that 4th shell, and its effective nuclear charge is going to increase, and that results in a shrinking of its radius to 133 picometers. Same thing with strontium. Strontium loses 2 electrons, and so it loses its outer row. Its effective nuclear charge goes up, and it goes from 215 down to 127. So cations are smaller than their neutral atom counterparts. Anions, on the other hand, are larger than the neutral atom. So chlorine, we're not going to be adding any more rows of electrons here. It's the same valence shells, okay? Both of these are going to have n equals 3. But chlorine neutrally is at 99 picometers. Chlorine anion is at 181 picometers. And that's because the effective nuclear charge is going to decrease. So the hold that the nucleus has on its outer row electrons is going to be less for the anion, so for chloride. And so that means, poof, this guy can expand out. Same thing with oxygen. It gains 2 electrons but keeps the same number of protons. So its effective nuclear charge goes down and its radius goes up. So when we talk about ionic radius from top to the bottom, so as we go down, it's the same rules as neutral atoms. We're adding more shells, and so therefore the radius is going to go up. So we're just talking about top to bottom, same general rules, Coulomb's law, adding new shells, forces of attraction. Okay, and same thing for the ionic radius of cation. So as we move from left to right, the radii of cations is going to decrease. So we're talking about the positive guys here. So if we talk about cations of, say, potassium versus calcium, which are right next to each other, okay, the radius of calcium is going to be smaller than potassium because it's going to decrease as we go from left to right. And that's because the number of electrons will stay the same as protons are added. So remember, potassium and calcium, when they get to where they want to be, they're isoelectronic, so they have the same number of electrons, but calcium is going to have more protons than potassium, therefore its effective nuclear charge is going to increase. Higher effective nuclear charge, higher force, Coulomb's law, it sucks it in, makes it smaller. Now when we talk about anions, these are the negative guys, so we're adding more electrons but keeping the positive the same. And so the second we add another electron, poof, it's going to get bigger. So when we go from left to right, the radius increases dramatically, not slightly. It increases exponentially, so it gets a lot bigger. And that's because of the force of repulsion between those electrons that we're adding without increasing the number of protons. And so the effective nuclear charge goes down, Coulomb's law, less attraction, it gets bigger. Okay, first ionization energy. We've talked about this before. It's just the energy required to remove the least tightly held electron, typically the valence electron, from an atom or an ion in the gas phase. Now, energy must always be added to remove an electron. So we talk about like sodium wanting to get rid of an electron. It doesn't really want to per se. It doesn't have the feelings like that, but it does take energy then to pull that electron away. So when something like chlorine reacts with sodium to take away its electron, chlorine has to put in energy to remove that electron. Okay. And here's just the first ionization energy. We've talked about it before. It increases as you go up and generally increases as you go from left to right. Now we'll look at another picture again, but you remember how it kind of jumps up and down as we go this way. That's to be expected, but the general pattern is it'll increase from left to right. And that's because the effective nuclear charge increases as we go that way, and so they're going to be more tightly held to the nucleus, Coulomb's law. It increases as you go up because they're getting closer to the nucleus as you go up, and so since these guys have a smaller distance, Coulomb's law, there's more force. These guys have a larger distance between the outer shell electrons and the nucleus. Therefore, it's going to feel a weaker force. So here's just that chart again. We can see as we go from left to right, it goes up, and then it goes back down when we go to lithium. And so here's what I was talking about. It generally increases. So from lithium to neon, the overall pattern is that it increases. But you can see like between beryllium and boron, it goes down a little bit. And you can also see how it increases as you go from top to bottom. So as we go from indium, which is the lowest, back up to beryllium or rubidium to hydrogen, it increases as we go that way. And that's because hydrogen, its outer row electron is going to be closer to the nucleus, so Coulomb's law, they're going to have a higher force. Potassium, they're going to be farther away from the nucleus, Coulomb's law, lower force. Okay, so a couple of reasons why there's blips. It does require more energy to pull an electron from a full D subshell than it does to pull only electron in a P subshell. And it requires more energy to pull an electron from a full S subshell than it does to pull only one electron, so the only electron in the P subshell when they're in the same period. So we keep talking about first ionization energy. There is a second ionization energy, which is sometimes referred to as the ionization potential. They're the same thing. So the second ionization energy is always greater than the first. So when we remove that electron, the positive stays the same, but we're losing some of the negative, and so therefore the effective nuclear charge always increases when we remove an electron. So it's generally easy to remove electrons until you get to the atomic or the noble gas notation that they want to be. So once they're isoelectric with a noble gas, it's going to be extremely hard to remove electrons. And so that's what they're saying here. So every element has one extremely large increase in ionization energy. So something like calcium that wants to lose 2 electrons, it loses its first one, pretty low ionization energy, and then it can lose its second one with also fairly low ionization energy. But once it's lost those 2, its third ionization potential is going to spike. It's going to go way up because it is happy. It is now isoelectronic with argon, and it doesn't want to lose any more electrons. And elements like chlorine and the nonmetals over on the right side of the periodic table, they're going to have very, very high ionization energies because they don't want to lose electrons. They actually want to pull them in. And so even their first ionization energy is going to be extremely high. We saw that in the other pictures. So we can actually figure out where an element is on the periodic table based on its ionization energies. So if you see an element that has 2 low ionization energies and then its third one is extremely high, that's going to be a pretty good indicator that it's probably an alkaline earth metal. It's probably in the second row because those are the elements that want to lose 2 electrons. Something that has 1 low ionization energy but the rest are high, it's probably going to be in the first row. Something that doesn't have any low ionization energies, it's probably going to be a nonmetal from the right side. And the last periodic trend is electronegativity. So electronegativity is the element's ability to attract electrons in a chemical bond. So when we talk about water, for example, hydrogen and oxygen, they're supposed to be sharing 2 electrons each. So that's what this line right here represents, 2 electrons that are shared between this hydrogen and this oxygen, and 2 electrons shared between this oxygen and that hydrogen. Now, share, we use that term very loosely. As it turns out, oxygen is much more electronegative than hydrogen, which it means that it has a stronger ability to attract electrons. That means the electrons that are supposedly being shared between hydrogen and oxygen are actually spending more time around the oxygen. So the electron density is higher up here. Electrons spend more time around oxygen because oxygen has a stronger pull, and it's more electronegative than hydrogen. So here's the general trend on a periodic table. So we can see electronegativity increases as you go up and as you go to the right. So if we put that in terms of water again, there's hydrogen, there's oxygen. So oxygen we can see is more electronegative than hydrogen. That's why it pulls those electrons away from hydrogen when it's bonding. Increases as you go to the right and as you go up. This isn't a 100% trend. It's the general increase from left to right. So we can always assume that anything farther to the right is going to be more electronegative than something to the left. And we've crossed out the noble gases here because they don't experience electronegativity because they don't bond. So remember the atomic radius trend, how it decreases as you go from left to right? So that means that oxygen's radius is going to be smaller than the elements to the left of it on the periodic table. Since it's smaller, that means it has a higher effective nuclear charge. That higher effective nuclear charge means that that nucleus has more ability to pull electrons towards it, and so its electronegativity increases. That's why, generally, the electronegativity and the radius kind of go hand in hand. So as the radius gets smaller, electronegativity increases because it's pulling them in, and it's just another aspect of Coulomb's law. Distance decreases, force increases, therefore it's going to be more electronegative.